Syllabus, books.
What book? Exactly. What book am I going to use? So I went to a professor who had taught this course before, and I asked him, what book do you use in this course? And he said, oh, in this book we have used, and those of you who've had physics may know that book, we've used Halliday and Resnick. It had been a classic for 20 years. It still is a classic. So anyway, I heard that in the US, students buy the textbook. Basically, I don't know how it is in Malaysia, but I grew up in the Netherlands, and you would never buy an introductory textbook for an introductory class. Why spend $100 or whatever it costs to buy a book if the professor is presenting the content of the book to you? But anyway, in the US, I was told that they all bought the book. And I was told to go to the bookstore and make sure that the bookstore had enough copies. So I went to the bookstore and I said, I will need 150 copies of Halliday and Resnick for my class. And as I walked back from the bookstore to my office, I said, wait a minute. If the students all have the textbook and I have the same book, then what do I do in class? So I stopped at my colleague's office again. I knocked on his door and I asked him that question. And he said, oh, don't worry. There are lots of different physics textbooks. And he showed me a shelf full of these big, fat physics textbooks. So I looked at them, and very quickly I found a book that was the perfect book for me. It was the perfect book for me for two reasons. One, it had a different approach. So it was not exactly the same thing as the book that the students had bought. But the second reason was much more important. The second reason was the book was out of print. Anyway, so for each class, I spent 10 hours preparing lecture notes from this other book. And in class, I would either put my notes on the overhead projector and project them on the screen, or I would write them on the blackboard behind me. And because my approach was a little bit different from what the students had in their book, I prepared copies of my lecture notes, which I prepared at the door so that when they walked out at the end of the class, they could take home with them a copy of my lecture notes. Now, why do you think I handed them out at the end of the class? That's right. I didn't want them to come in the morning, take the notes, and go back to bed. But isn't that already admitting that there's something wrong? Why prevent the students from getting the information out of the lecture notes if they could get it? Why force them to come and listen to me, right? If they could get the same information from the notes. That never came up in my mind. But what did happen was that after a few weeks, some students came to me and they said, Professor Mazur, could we get a copy of your lecture notes at the beginning of each class? This way we don't have to write down that much. And I had indeed noticed that each time my pen went A on the blackboard, 150 pens went A in the notebooks of the students. I once heard somebody describe the lecture as a process whereby the lecture notes of the instructor get transferred to the notebooks of the students without passing through the brains of either. And that's precisely what was happening in my class. So I decided to start handing them out at the beginning of each class. And much to my relief, the students didn't come in, grab the notes, and go back to bed. No, they came in, grabbed the notes, they sat down, and they still copied everything I wrote down because they had no time to read the notes. Anyway, I got my high evaluations at the end of that first year. And you know what happens when you get a high evaluation? You get punished. They ask you to teach the course again. So I got asked to teach that course again the next year. And I said to myself, you know, rather than handing out these notes class by class, I'm going to take the whole collected set 1 week before the semester starts, send it out for duplication, and on day one, the students get the whole packet for the entire semester. You know what the unexpected result was? The unexpected result was that about half a dozen students wrote in their end of semester evaluation, "Professor Mazur is lecturing straight from his lecture notes." Hello? I mean, what was I supposed to do? Prepare another set of lecture notes that was different from the lecture notes I handed out? I was livid. These ungrateful students. But you know, the students had a point. I was lecturing from my lecture notes. I was, in a sense, a reader transmitting printed information to the students. But it took many more years before I finally figured out that that was what I was actually doing. So let me ask you the following question then. Given that this approach is being used all around the globe to teach many, many different disciplines, is that what education is? In other words, is education simply the transmission of information? Let's do actually a quick vote here. Since we have these clickers, I can start a vote. If you think education is just the transfer of information, you press 1. If you think there's more to education than just the transfer of information, you press 2. So go ahead. Okay, let's see. Let's project the distribution. Look, 94%. I don't know what answer number 5 does here. It's either yes or no. I mean, 5%, or about 10 people, chose yes. To those 10%, I say, your job is on the line. Because, look, if we have lots of evidence that education cannot be just the transfer of information. For if it was the transfer of information, then this university and your job and my job would be in great trouble. Because we now live in an information age, and there are plenty of ways of disseminating information. Think about it rationally. Why are we reenacting the same lectures over and over and over every year? What about just filming it and making it available on the internet, and students can download it whenever they want and look at it in, 7-minute batches or 15-minute batches or 1 hour, whenever they want, whenever they're ready? What would you lose? Well, you'd say you lose the interaction. But how much interaction is there in a real lecture? I've made a habit of doing what I call academic tourism. I'll just go around campus and I'll just stop in a random class, step into the back, and observe the activities. And invariably, it's the same thing. A professor in front of the class who talks and talks and talks and talks, and students who either sleep or take notes. Or now that there's wireless and computers, they do their email or Facebook or YouTube, and while the professor is standing in front of the class. Now imagine you were to film that and make it available. What would you lose? Well, you say the interaction, but how many students raise their hand and say, "Professor, could you please stop talking for a moment? I need to think." That never happened to me, I can tell you, and I've taught for close to 27 years at Harvard. Or a professor or a student who says, "Could you explain this again? I didn't understand it." That has maybe happened once or twice in my career. But once or twice in 27 years, right? I mean, I think you would lose very, very little. Whereas if the student were to be able to watch the video, he or she could stop whenever doesn't understand something and think, let me think about this. Or rewind and listen to it again. Or call up a friend and say, "Hey, did you understand what Professor Mazur said there at 3 minutes and 25 seconds into?" Right? I mean, you'd actually have a benefit there, right? Because the students can do the learning when it's convenient for them rather than for us. But we know that that is not going to replace education, or at least we hope, because otherwise we're in trouble. there won't be any universities later on. So given that 95% or 94%, I still don't understand this 5 here, 94% has answer number 2, now I have you in a corner because now you have to tell me what it is that is missing. If education is not just information transfer, of course, information transfer has to be part of it, right? No information transfer, no education. I agree with that, right? No information transfer, no education. But it's not enough. It's not enough. And you know, let's face it, let's look at the history. Why did this model develop? Well, before the biggest discovery, the biggest breakthrough in information technology, the lecture was the only way of transferring information. Which discovery am I referring to? The book, exactly, books. Right? Before books, it was impossible to transfer information from one generation to the next. There was no choice but to put the sage on the stage delivering information while other people were as scribes scribbling down, right? It was the only way of disseminating information. 1498, Gutenberg invented the printing press. Why didn't that affect education? Well, because books were not a commodity. They were very expensive. Few people could afford books. It was not until the Industrial Revolution, about 100 years ago, that books became a commodity. So at least until 100 years ago, this was an absolute necessity. But now we have not only books, we have computers, we have smartphones. Information comes at us from everywhere, right? So what is it that is missing? What else needs to happen to educate people?
The wisdom.
Understanding?
The wisdom of the professor.
The wisdom of the professor. Well, I don't know. We'll get back to the wisdom of the professor in just a second. To construct the information. New ideas. Let's go back for a moment to the little exercise we did at the beginning, right? What was the most popular choice? Practice. You need to practice in order to learn, right? You need to practice in order to do something useful with that information, which comes back to constructing knowledge. Right? You need to take, as a learner, you need to take that information, connect it to what you already know, and connect it to your experiences in order to make sense of that information. Right? Information by itself is worthless. However, and I'm exaggerating maybe a little bit, but I think I'm not exaggerating very much, by saying that a lot of education is simply this following model. The instructor delivers information to the students. You wait 2 months, and then you have an exam where the students is cut off from all sources of information, and the students just parrots the information back to the instructor. That's how I learned history. I had to memorize all kinds of dates of events. Right? French Revolution that year, this Napoleon defeated at Waterloo that year, and so on. And then on the exam, there would be a question that said, in what year was Napoleon defeated in Waterloo? 1812. Most of the things I've actually forgotten because I just picked one that I remember, but most of them I've forgotten. It would have been much more interesting to think about what the causes were for those historical events. Why did they happen? How could we prevent similar type of events from happening in the future? Or maybe foster that type of events if they're positive ones. Learn about the socioeconomic conditions that led to those events. Right? But missed opportunity was simply the professor giving, in high school and in college, the professor giving information to me, and on the exam, I just gave the same information back to the students. You know, we want our students to do more than that. We want to do and to use that information to solve the problems that society faces. Energy, environment, conflicts, you name it. Problems that we cannot solve. So we just heard somebody say something about the wisdom of the professor. I want my students not only to come up to my level, I want my students to stand on my shoulders. I want my students not just to be able to recite the information I give to them or solve the problems that I have solved for them. I want my students to solve the problems I cannot solve. We want to have the next generation stand on our shoulders and do more than we can do, right? Not just have them parrot back what we can do. Unfortunately, I think most, and this is not a big exaggeration, I think most education is simply, I give you information, you give it back to me. I show you how to solve a problem. A few months later, you show me how to solve that problem. No wonder students tend to be not very innovative. No wonder we don't stimulate creativity. In fact, we stifle it that way. Right? No wonder people are not motivated and inspired by most education. Anyway, so lectures focus on information transfer, but education is so much more than information transfer. And the fact that that was a fact became clear to me when I gave the FCI, the Force Concept Inventory, for the first time to my class in 1990. Actually, this is pre-test data that I'm going to show. So I cannot be responsible for that. This depends on what they've done before they come to my class. The FCI has 29 questions. So on the vertical is the number of students who obtained a certain score. So here you can see in 1990 there were 2 students who got 29 out of 29 on the first day of class. Full score. When I took the test, I got 28 out of 29. I think I misread a question or something like that. No, I actually made a real mistake. Hestenes says that anybody who scores below 23 is still partially an Aristotelian thinker, connecting force to velocity rather than acceleration, just like Aristotle did during the ancient Greek. And as you can see, 70% of my class, before I teach them, is still an Aristotelian thinker. These are Harvard students. They've already had 2 years of physics in high school. And they probably had the top grades, otherwise they would not have gotten into Harvard University. If you take a gorilla and you put the gorilla behind the keyboard randomly pressing buttons, the gorilla will get about 10. As you can see, some Harvard students belong in the zoo. But again, I cannot take any responsibilities for this because I haven't taught them yet. So let's see what 1 semester of award-winning teaching by yours truly does to change this distribution. Are you ready? Here we go. Well, at least there's an improvement. So I discarded that very quickly too. And then as I was struggling with this, I came up with the perfect excuse. I'm just telling you this because I want to show you how hard it is to realize that actually the culprit is you, in this case me, not anything else. So I tried to avoid that as long as I could. So it's not me, it's not the students, what else?
Question.
No, what?
Question.
I want to hear more. The questions, the test, exactly. Usually I have to work much more on the audience. You're very sharp here all. Exactly, the test. There has to be something wrong with the test. I mean, think about it. Heavy truck, light car colliding head on. Would you rather be seated in the heavy truck or in the light car? Right? I mean, I think everybody would choose the heavy truck. So maybe it was not a matter of understanding, but simply, you know, misleading words. They were trick questions. After all, if I asked them a textbook problem that involved Newton's third law, that'd be fine. FAB equals FBA, no problem. So I thought, there's something wrong with the test. And I decided to do some testing of my own. I'm going to show you a little bit more physics here. How many people here are in engineering and/or physics? Can I see a show of hands? This is a technology university, right? Is everybody else in the humanities? Or are people just too afraid to raise their hands? Here, we'll do it anonymously. Let's see. Here. If you are in engineering or physics or another science-related field, press 1. If you're in a field that's not science at all, press 2. And if you press 5, I don't know what that means. Okay, let's look at a distribution. Okay, so we have 2/3 of the people here who are in science and technology fields. Okay, so I'm going to show you a little bit of physics, and the people who are in that first bar there, the 64%, will be able to follow what I'm saying. The others might have a little bit of trouble, but that doesn't matter, because it's not about the physics. What I'm going to tell you now is about assessment. How do we assess our students? And I apologize for putting it in the context of physics, but that's the only thing I can do because I am a physicist. Okay, so I decided to do some testing of my own, and I decided to do that on the midterm examinations, not on multiple choice, not on the final examination. So on an exam, I put 2 questions on exactly the same subject, electric circuits. One problem was straight out of the textbook. It's behind me on the screen. You have 2 loops here and 3 resistors and 2 batteries, and the students were asked to calculate the current in the 2 ohm resistor here and the potential difference between point P and Q. I could ask the 64% here who didn't raise their hands but press 1 to solve this problem, and I could do the same thing here, you know, spend 10 minutes working it out. It's about what? 2/3 of a page of equations. And then we could compare our answers, and I'm sure many of us, including myself, would make a mistake somewhere, because it's very difficult for 2/3 of a page not to make any mistake at all. This was problem number 5 out of 5, so the last one on this midterm examination. On that same examination, I put this question. 3 identical light bulbs, A, B, C, are connected one after the other in series to a battery. Just like the lights in a Christmas tree, you know? And then there's this switch S, which provides a short. When you close it, it provides a short, shorting out the last light bulb. Don't do this at home tonight, it's dangerous, okay? When you short out one light bulb, all of the current goes to the short, because this has no resistance. This has resistance, so all of the current goes out. So it's like having 2 light bulbs connected instead of 3 light bulbs connected. That's all there is to it. So the questions that I asked the students were the following. When that switch S is closed, what happens to the intensity of light bulbs A and B? And the only thing the students had to say was it increases, it decreases, or it stays the same. That's the only thing they had to write down. What happens to the intensity of light bulb C? What happens to the currents through the battery? The potential differences across the 3 light bulbs? The total power dissipated. To answer this question takes about, if you understand circuits, and I don't expect you to, but don't worry, I won't ask you. If you understand DC circuits, it takes 30 seconds to answer this question. And of those 30 seconds, 25 are spent on part E. The rest is just, you just answer it. Now, what I didn't tell you is that large courses at Harvard are team taught by 2 professors. So in order to put this on the exam, I had to convince my senior colleague, because I was still, I think I was associate professor or assistant professor at that time, I had to convince him that this was a good problem. So I went to his office, was a handwritten version of this problem, and I showed it to him, and he looked at it, and then he looked at me and he said, "Eric, you're out of your mind." I said, "No, I don't think so." And you know, he had not been part of the fall semester, so he didn't know about the FCI and so on. So I explained to him about the FCI and how I had struggled with the results, and I wanted to understand the difference between students' performance on word-based questions and on textbook problems. And he listened patiently, and then he said to me, "But Eric, we only have 5 problems on this exam. We cannot give away 20%. He considered this such a trivial problem that it was just like giving away 20%. I said, Well, I hope we're giving 20%, but I'm not sure. You see, I had been the one who had taught this subject, so I thought it was my prerogative to determine how we would examine them. Anyway, we argued for about half an hour about this, and finally he reluctantly agreed to put this on the exam, mostly because we didn't have any other problem. We made this problem number 1, you know, the warm-up problem. Well, it turns out the students overheated. Professor Mazur said one student, this problem number 1 was the hardest problem on the exam. Or another student who said, Professor, I didn't know how to get started on this problem. What do you mean getting started? If you're started, you're done, right? It's just a one-step thing. I decided I would grade this problem. We had about 250 students, but remember, I told the students just to write increase, decrease, stays the same. So I thought, you know, I could, what, in maybe an hour and a half, quickly go through it, right? Increase, right? And next exam, I mean, I thought I could fly through it. Big mistake. It took me an entire weekend. Why? Because the students had freaked out. Some had written 6 pages in their examination booklets, writing down everything they knew about DC circuits, hoping to somehow say the right thing. And I had to read it all. And by the time the grading had been completed, it was clear we had a problem. On the conventional textbook problem, on the right there, no, sorry, on the left there, that's the problem when you're with your back to a screen. You forget what is left and right. On the left, you see that the average is about 7 out of 10. So they did quite well on that textbook problem. On the conceptual one, the 3 light bulbs, the average was only 5 out of 10. I can't, since there are so many people in science and technology here, I can't resist explaining about this peak here. Do you see that? About 80 students got 2 out of 10. You know why? Because I'd written down so much, I was able to reconstruct their thinking. So let's go back to the problem. 50% of my students, Harvard students, made the same incorrect assumption. They said, when the switch S is closed here, nothing happens to the current here. After all, it hasn't gotten there yet, so it doesn't know the switch is open or closed. That's wrong, right? Because if you close this switch, you basically have 2 light bulbs connected instead of 3. 3 light bulbs has more resistance than 2, so you get more current. So they lost 2 points there for part A. What about part B? Well, when the switch is closed, the current arrives at this junction just as it did before. But now, in addition to being able to go straight, it can also take a right turn. So the big question is, how many electrons are taking a right turn, and how many are going to go straight? I already told you the real answer. They all take a right turn, because that is the path of no resistance. But what do you think 50% of my students assumed? 50-50, exactly. Half of them are going to take a right turn, and half are going to go straight. And you know what? Let's see what that gives for answer number B. So half goes this way, half goes that one. So the current through C goes from the original current to half its value. So what did they write down? They wrote down the intensity of C decreases. You know what? That's where they got their 2 points. Of course, it goes out, but that's decreasing too. So I had to be fair and give them their 2 points. So actually, it's a lot worse. That whole peak of 80 students should really be 0. These are Harvard students, pre-meds. Some of them are going to do bypass surgery later on. I'll tell you, same principles. Anyway, because it's the same students on the same day, you expect there to be some correlation. You expect that the students who do well on one type of problem do well on the other type of problem, and students who do poorly on both. So let's plot for every student the performance on one type of problem versus that on the other. And you know what? I'm afraid there is no correlation at all. The data are all over the place. Which shows that the picture we get depends on the assessment. Right? Depending on one type of assessment, you get a very different picture than on the other type of assessment. And we're fooling ourselves to believing that we can honestly assess students' performance. Well, this shows that at least I wasn't capable of doing that at all. Okay, but if you're willing to relax your definition of a line a little bit, you find that about 50% of the students do equally poorly or equally well on both types, right? These students here. But now look here. 40% of students lies below this, meaning they do well on the textbook problem, but they don't do that well on this word-based problem. There are actually 6 students, this represents 6 students on top of one another, who get 100% on the textbook problem. They're not even able to get their free 2 points. Right? We already knew this, but now look here. This is empty. It's totally empty here, meaning students who get the word-based problem right, who think about it correctly, get a high score on the textbook problem. Let's go back for a moment to these 39. That makes sense, right? Because you understand it, you do well on the textbook problem too. But let's go back to these 40%. 40% in my class at Harvard. What are these students? Who are they? Why are they there where they are, below that line? What are they doing? Memorizing. Memorizing by rote. They have an approach to solve the problem. Let's put ourselves in the mind of those students, right? You come to the exam. I'm sure you remember taking exams, right? Sitting down in a classroom not very different from this one. You have to leave one seat free between you and your nearest neighbor. The professor and his teaching assistants are handing out the exams. Let's pretend this is an exam. It's printed side down, right? Because everybody has to start at the same time, right? You're still looking in your book, you're sharpening your pencils, you're quickly looking through your notes to make sure that the last bit of information sticks into your brain, right? And then at one point, the professor says, please put your books away and be silent. The level of noise in the room goes down. Your heartbeat goes up. You remember those instances? I do. And the professor says, you may begin. And you hear 150 pages being turned around. It's silent, but you can hear the sound of paper being turned around. And as you turn this page around, you see that figure. You have not yet read the words, but you see that figure. We're talking here about the first 500 milliseconds, right? I mean, turning it around, see that figure. What is the first thought that crosses your mind as your eyes see that figure? This is a question to the engineers and physicists here.